Hello, I'm Jonas, the creator of VHDLwhiz.com. Today I'm going to show you how we can create a VHDL controller for an RC servo. And the servo that I'm using is this one, TowerPro SG90. And this is a fairly common servo for radio-controlled cars and aircraft and all kinds of radio-controlled toys. But the VHDL module that we're going to create now in this video is going to work with any RC servo that uses PWM, and that's most RC servos. They use PWM to control the position of the servo. Now, I'm referring to the blog post that is linked to from the video description, so if you want to read in detail about what I'm talking about in this video and even download the code projects for ModelSim and for Lattice IceCube, then go to the video description and click the link to get to this blog post. So this is the blog post, RC servo controller using PWM from an FPGA pin. So how does this work for RC servos? Well, this is an old protocol which has been used for a long time by RC servos. And the way it works is that the RC servo will only look at the high period of the input signal. And this duration, the duration of this high period corresponds to a position on the servo. So for example, if the pulse on the high period on the input PWM signal is 1 millisecond wide, then that might correspond to 0 degrees. And if it's, for example, 2 milliseconds wide, then that might correspond to 180 degrees. And everything in between that are positions between 0 and 180 degrees. And the period between the high pulses is of less importance. It is of less importance. So a common value here is 20 milliseconds, so that we refresh the servo position 50 times every second with 50 Hertz frequency. But this value is not very important, but the duration of the high pulse is important because this is what controls the position of the servo. So I have already downloaded the zip file that you can get by entering your email address in this form, need the ModelSim project files, and by clicking give me the files. So I already have this zip file, so I'm going to unzip it right now and we're going to take a look at the code. I'm unzipping the zip file and going into the zip folder or the folder. And here we have a folder named Lattice IceCube 2 project, and this is for the Lattice IceCube FPGA software. We have a source folder which contains the VHDL files, and we have some usage explanations, the ModelSim project files, and the run script for ModelSim and the wave file for ModelSim. So I'm going to right click on the source folder and select open with code because I have VS Code installed on my system. And now I have opened the folder and I'm now looking at the servo module. And I'm just going to go briefly through how it works. So we have the entity here with a generic declaration. So we have declared a bunch of generic real types and one positive or integer number. So because this module is going to work with any FPGA and with any PWM enabled RC servo, this module has to know the clock frequency. It also has to know the pulse frequency of the PWM signal. So that's how often these pulses arrive. So I'm going to use 50 because that corresponds to the most common value for RC servos, 20 milliseconds between them. And then you have to specify the minimum pulse duration and the maximum pulse duration in microseconds. And to get 1 millisecond, you enter 1000 on this generic, and to get 2 milliseconds on the max, we can enter 2000. But I have used some different values because these values didn't work perfectly with this servo, but we can configure this to work with any kind of servo. And also step count is the last generic input, and this defines how many steps is there going to be between the minimum position here and the maximum position. For example, if there are only 3 steps, then it's only this position and that position and this position. But we can use as many steps as we want because this code is configurable through generics. Finally, we have the port declaration. Of course, we have the clock input and the reset input and the position input as an integer from 0 to whatever value you set on the step count. So we're going to use 0 to 255 in our example. And the last signal on the port is the PWM output. And that is the signal that goes out from the FPGA, goes to the signal line, this yellow line on the servo, and it controls the position. So that's the PWM output, which the servo will sample and set the position according to. Now, this module uses only integers to work, so it will work on any FPGA. It doesn't use floating point numbers because all of the calculations are done in the declarative region at compile time or simulation time. And I'm using a function here to calculate the number of clock cycles that we have to wait for each microseconds, because we specified here the number of microseconds that the minimum pulse time or the maximum pulse time should be, but this is of type real, and this type, the real type, can't be synthesized, so we have to translate it to integers, and that's what this function is going to do. So at first I translate the minimum pulse time to an integer, the maximum pulse time to an integer, and I call them min count and max count. And also I calculate the number of microsecond difference between the min and max pulse, and we use it just on the next line to calculate the step count. So how many microseconds is it between one position step and the next closest position step. So these are intermediate values, still real types. And then finally we are using this step microseconds variable or constant to calculate the number of clock cycles we have to count to go from one position to the next. So how many more clock cycles do we have to count to go from the 0 position to the 1 position, so the extra number of clock cycles for each position. Now we're going to use this constant and this constant in the implementation now to create a module that works only by having counters and multiplexers and registers. Okay. So to do that we need to have a PWM counter, like a wrapping counter, which just counts clock cycles continuously. And I'm basing this one on the pulse hertz generic input. So that's the generic input that defines the period of these pulses, because we have to count from there to there, from the start of this pulse to the start of the next pulse, just to make sure that they are spaced evenly apart. Okay, so then this counter has to be that wide, and I'm making this new counter. And also we are making a new signal, which is a copy of this counter, but we call it duty cycle. And when the duty cycle is less than, or when the counter is less than the duty cycle, then it means that we are in a high pulse, and if not, it means that we are in a low pulse. So I talked about this in an earlier article about PWM. You can get to this one by clicking this link, but I have already covered that, so I'm not going to talk about that. But if you're interested in learning about PWM specifically for any application, then just go to this article. Okay, so let's look at the implementation of this module. So this is the first process. This is just the counter process which wraps this counter. So it will wrap this clock cycle counter every time a new pulse is going to start. So it's going to measure the time from there to there based on the generic inputs. The next process, the PWM process, is what sets the actual output signal, the PWM signal that goes to the servo. So in the beginning it's going to be 0, and because that's the reset value, and I'm going to assign a default value of 0. But if the counter is less than the duty cycle, then we're going to set PWM to 1. So you see, then the value of this duty cycle decides if the PWM output is 1 or 0. It's going to be 1 at the beginning of the counter, and when the counter exceeds the duty cycle, then it's going to be 0. And that's how we create this PWM pulse with the correct duration. And finally, this is an important process, the duty cycle process, which sets the duty cycle. So the duty cycle controls the duration of this pulse, as I just said, and this final process controls the duty cycle signal. And I'm setting it to reset value min count because the duty cycle is never going to be, or the PWM pulse is never going to be less than the minimum period, because that's the position 0. And then I'm using the position input, so this is the one that comes from the port input. I'm using this one to calculate how many clock cycles we have to wait, or how many clock cycles the duty cycle is going to be. And this position input is controlled by the user of this module. And the way we calculate it is simply by multiplying position by our cycles per step constant and adding minimum count to it. So if we are at 0 position, then these are gone and it's only minimum count, so then we are outputting this value. If we are at the maximum position, then it's going to be minimum count plus the max number of clock cycles. So then we're going to output this max duration pulse. So that's how this module works. So I have already created a test bench for it here, and you can use this test bench if you have downloaded the zip file. It instantiates this module, this servo module here, with generics that are quite small, like the step count is only 5 and the clock frequency is only 1 MHz, and that's because I want this simulation to proceed quickly. So we can go ahead and try this test bench. I'm not going to explain the test bench in detail, but I explain it in the blog post, and you can look at the code yourself if you download it. So I'm going to run this test bench, and keep in mind that I have just downloaded the zip file and unpacked it. So if you do this same thing on your computer, you're going to have the same results. I'm typing do and the path to the downloaded folder. It's users, my username, downloads. Then I have to go into the RC servo folder, which I unpacked, and run the run.do file. Do and path to the run.do file, like this. So now all of the files were compiled. We can see by the green ticks here, and there's a user manual. Thank you for downloading this example from VHDLwhiz.com. Type run TB to run the test bench, like this, run TB. So let's just do that. I'm typing run TB, enter. You see how quick it is to run my examples. So most of my blog posts, they have downloadable zip file with a ModSim example, which you can run like this. It works on Windows, it works on Linux. And this is how you do it. Just load the run script and type run TB. And it's a bit slow, this simulation, but it completes. It has completed now. And it's slow because there are many clock cycles, and that's why I used the low values for the generics, because if I didn't, it would be even slower. So the position here can be from 0 to 4, because it's 5 steps. Position 0, 1, 2, 3, and 4. And here we can see the counter, the internal counter in the servo module. It's counting from 0, and then it goes to the max value, and it wraps back to 0 again. And we see the duty cycle is set accordingly. So for each position it increases. And we can also see here that the duration of the period here, it increases as well. So for position 0, let's check the duration. I'm going to place a new cursor here. So now we have two cursors. Place one at the rising edge of the clock or PWM pulse, and one at the falling edge. And we can see here it's 1000 microseconds, and that's what I specified in the test bench here. Pulse width min 1000 microseconds. And then we can go check the max duration. Let's see what that is. Placing the cursor at the falling edge of the PWM pulse when the position is at the max value 4, and we can see here that the pulse width is 2000 microseconds, and for all of the values in between, the positions in between, the pulse width is accordingly shorter, or something in between 1 and 2 milliseconds. Okay, so that's the simulation of this module. I have also created the implementation for Lattice IceCube. So I have set some output pins. So that's pin number 119 for the PWM output, and I've set the clock period. So I have a project for Lattice IceCube here in this folder, Lattice IceCube 2 project. So I'm going to open IceCube 2. I already have it open, but there's no project loaded. I'm going to click the open folder here, go to the downloaded zip file which I extracted, go to Lattice IceCube folder. Then I'm going to open the IceCube project, servo spt.project. So this is the project that I have prepared for implementing this on the FPGA. So I'm pressing OK to open it now. And nothing is run right now, so I'm going to go to Tools, Run All to compile and create a bit file. So we're going to see what happens now. So it's compiling now, and what we're going to do now is to implement it on the Lattice iCEstick. And the 119 output pin is this one, the lower left header pins. These are solder-on header pins, and this is the one that has the PWM output, which I've assigned it to. So now the router is running. And we are waiting for the bitmap to be generated, and we can see a bitmap has been generated. So it's time for us to program the FPGA, and I have already loaded the Diamond programmer. Let's see, there it is, Diamond programmer. And I'm going to open the Diamond programmer project file which I have prepared. So it's in the same Lattice IceCube 2 project folder. From the zip file, and just click the diamond.xcf file and click open. And when you click OK now to open this programmer project, Diamond will be loaded with all of the settings for the Lattice iCEstick. But you have to do one thing before we can program the FPGA. We have to select the file name of the bit file, because that's not possible to include in the Diamond programmer folder or project. So I'm going to click these three dots, and now we are, where are we now? Let me see. Yes, so we are in the RC servo folder. So I'm going to go into the Lattice IceCube 2 project, go into the next folder, which has been automatically generated by IceCube 2 now. Go into SPT, go into outputs, go into bitmap, and then I'm going to select top bitmap pin, okay? So I'm going to select this one. And I'm going to plug in my FPGA now. I'm going to plug in my USB cable here. I'm going to plug it in, of course, on the FPGA side here. Just like that. So now I'm pressing program in Diamond. And we're going to see what happens. operation success. So that means that the bit file has been programmed on the FPGA. And now, before we plug in the power now, we're going to open or power on my oscilloscope right now. We're going to check the outputs from the FPGA. This is a cheap oscilloscope which I have laying around. So I'm plugging in the ground cable and I'm plugging in the I'm selecting the FPGA output just like that. So there we go. You can see here that the PWM output is working. Let me just move this trigger position so we can see the whole pulse like this. There we go. Yeah, so I can place, for example, 2 cursors. Can I do that? I'm going to place one. Oh, I have the other cursor. Yeah, this is. I'm going to place one cursor at the start of the pulse. I'm going to place the next cursor at approximately the end of the pulse, when it's at the max value. It's about there. We can see here that it says 2.5 milliseconds. I'm going to show you my code now in the top module, because we haven't talked about the top module, but it's a bit too much for this video. But what I'm doing inside of here is setting the constants. Min pulse 500 microseconds, so half a millisecond, and max pulse 2500 microseconds, so that's 2.5 milliseconds. And that's exactly what this oscilloscope is showing for the max pulse. Let's also check the min pulse now. I'm going to go to approximately where the PWM output is at the lowest level. 500 microseconds. You see that? It says here 500 microseconds. So that matches exactly the values in my code here. And you may be wondering why it's going up and down like this in a nice smooth fashion. That's because I'm using, in my code, in the top module, I'm using the sine ROM from an earlier blog post. But that's something else. I'm not going to discuss that in this video. But if you want to read more, I have a link to this article which explains the sine ROM. That's why it has this nice movement up and down, because it's a little bit because I'm using the sine wave to control the position input to this servo. Okay, but there's one thing remaining. We have to try to connect the power to this servo and see what happens. So I'm connecting the 5 volts now to the servo, and there we go. See that? It's working. So when the PWM output is at the max value, then the position is all the way to the counterclockwise. So it's the opposite behavior that I described in the beginning of this video, but that doesn't matter. It's going 180 degrees. So when the PWM pulse is 500 microseconds wide, then the actuator is all the way to the left. And that's how you can easily create a PWM controller for an RC servo in VHDL. Now you can go ahead and download the code from the blog post, and you can try it for yourself if you have any kind of RC servo laying around. It's quite easy actually. Did you see what we did now? We used the constants and the calculations in the declarative region of the module, so that if we look in the synthesized netlist now, we're not going to see any DSP or anything like that. It's only going to be counters and multiplexers and registers, because we are taking care of doing all of the calculations at compile time. So It's really a quite simple module. The logic is quite simple because all of the difficult calculations, we're doing them at compile time, at synthesis, and it doesn't go into the FPGA. What goes into the FPGA are just simple counters. So that's I like the beauty of this module. It does what it should, and it's very configurable, so we can use it with actually any servo. Okay, that's all that I had for you in this video. Go ahead and leave a comment on this video or in the blog post, or if you're having any trouble at all, just leave a comment on the blog post. Thank you for watching, and until next time, keep coding.